Morning students, in the previous video session you have gone through the electrostatic potential energy for collection of point charges, and I have told you to write all these in your notebook and learn it. Now let us see what will happen to this electrostatic potential energy when a dipole is kept in a uniform electric field. So yesterday we have seen many charges kept in an arrangement, and there we have found out the electrostatic potential energy, and now we are going to see what will happen to this electrostatic potential energy when it is kept in a uniform electric field. Uniform electric field means this is uniform electric field. Already you have discussed like this one question. A dipole is kept in a uniform electric field so that it produce what a torque. Already you have discussed after the equatorial plane, axial line and equatorial line, two derivation you have learned. After that you have learned this also, like this one. Dipole is kept. Dipole means two equal and opposite charges. Here minus q, here plus q. This is what we can tell dipole. So two equal size and opposite charges constitute what a dipole. And so what will happen means these are the component value 2a sin theta and 2a cos theta, and already you have gone through this. I will tell you the topic after this equatorial plane, torque experienced by an electric dipole in the uniform electric field. There you have got on formula 2qa sin theta, and torque is equal to p vector into e vector. Like that you have solved on formula also. Torque experienced by a dipole in an uniform electric field. So you have learned that if there is a dipole kept in a uniform electric field, it experiences a torque, and that torque also you have learned that torque is equal to what? The torque is equal to p vector into e vector. Like this you have learned on formula also. Torque is equal to Pe sin theta you have learned. So this is what a torque formula, and based on this we are finding the electrostatic potential energy on this dipole when it is kept in uniform electric field. For that here this diagram you can explain. Consider a dipole which is placed in the uniform electric field. Now what will happen? This dipole will experience a torque. Okay, so first point is what? One dipole is kept on uniform electric field so that it experiences what? Torque. So what will happen? This torque rotate the dipole within the direction of electric field. This thing, electric field line which is moving from here to here, positive to negative. So here positive charge means it will go towards negative side, and here negative charge means this is positive charge, isn't it? So it will go this side. So it will, what will happen? It will rotate. No, now it is like this. So assume that here at this end there is a force this direction, and this point there is a force this direction, and another end there is a force opposite direction. So that what will happen? This dipole will rotate like this, and this dipole will rotate. So this dipole will rotate and it align with what? This electric field line. So once it aligns with the electric field lines, what will happen? Uniform electric field line stops its rotation. So what will happen means we have to find out the electrostatic potential energy on this dipole, so that here some external torque is applying to rotate this dipole at constant angular velocity. So what it is doing, there is an external torque. So there is an external torque is applying. External torque is applying for what? To continuously rotate or to move at constant angular velocity from one angle to another angle. That angle we can take is from one angle theta dash to theta. Okay. So this is theta you can keep. So I am applying on external torque to rotate this dipole at constant velocity from angle theta dash to theta. For that, what I am applying? An external torque. Okay. Now you can write an equation. Okay. Now you can write an equation. We know that when it is moving, when this dipole is rotating at constant velocity, constant angular velocity, there must be some work has to be done. That work done we have to find out, and that work done is equal to what? Electrostatic potential energy. Electrostatic potential energy. So let us find what is this work done. So we know that the basic formula W is equal to F into D. W is equal to F into D, and W equal to F into D means this force and this D distance, this formula we are using for linear velocity. Linear velocity. Normally one object is moving in a straight line. That one work done we are finding by using W is equal to F into D. Now here we are using W is equal to what? Here force is what? Due to this torque. So torque external force into distance. Here the distance is what? Variation in the angle. You see, when this dipole is rotating, every time theta is changing. So theta is changing from theta dash, one angle to another angle. So that here you can write d theta. Now this is the work done formula. We know that the torque formula already we have learned. This you can keep one. Torque we know. Torque formula is 2a QE sin theta. This is what through the last derivation, torque experience in an uniform electric field, you got this formula, and we know that torque external torque is equal to 2AQ. 2AQ means P sin theta. So 2AQ means what? P. Dipole. That is what? Dipole. 2AQ means dipole. Now from this formula you can write in a vector form P cross E. This is vector form. So this is a vector form. Torque is equal to P cross E. Now this you can take equation 2. So substitute 2 in 1. So that W is equal to, instead of this torque, you have to put this PE sin theta, then d theta. Now we have to find out, this is the work done for what? Only, you know this, dipole is like this, it is rotating like this. When it is rotating, this d theta means there is a small rotation, only this much is d theta. But we have to find out here we have to find out the work done to rotate this dipole on this, on what for this whole rotation. Whole rotation means from theta dash angle to theta angle rotation we have to find out. So that integrate this equation. Integrate equation 3. So W is equal to PE sin theta d theta. You will get here limit theta dash theta. Now W equal to P is common, E is common, constant. So integrate only sin theta d theta. We know the integration of sin theta d theta is minus cos theta. Put the limit theta dash theta. So sin theta d theta is minus cos theta. Okay. Now next step, W is equal to PE. First apply the upper limit, then lower limit, minus cos theta. Applied for upper limit, then lower limit apply, minus of minus cos theta dash. So upper limit minus lower limit, that is how you will apply the limit. So here upper limit is theta, lower limit is theta dash. So minus cos theta minus, then this minus cos theta dash. So W equal to P E. So W is equal to P, then minus cos theta, minus into minus, plus cos theta dash. Multiply this P inside, so W is equal to minus P cos theta plus P cos theta dash. So work done is equal to the water change in potential energy difference. So that you can write this is what you can write this equation you can write like this also. W is equal to P cos theta dash minus P cos theta. So this is what a change in potential difference delta U we can write. So work done is equal to the change in potential energy delta U is equal to this, instead of minus P cos theta you can write what U theta, and plus you can write what here minus is there, plus you can write U theta dash. This you can change and also write delta U is equal to, you can write what U theta dash minus U theta also you can write anyway you can write, it is not a problem. This is equal to what this equation, minus P cos theta plus P cos theta dash. So this is what potential energy. So when we are keeping a dipole in an uniform electric field, the potential energy is what U is equal to, what you will get U is equal to PE cos theta plus minus P cos theta plus PE cos. So we got this equation PE cos theta dash. Now so U is equal to, we got the value, now we got the electrostatic electric potential energy. Now let us see what will happen. We know this thing, one thing, first thing, when theta is equal to theta dash, assume that we are keeping this dipole the initial angle, the theta dash, initial angle 90 degree. So initial angle 90 degree means from our formula. This is our formula. So delta u. So you can write u theta minus u theta dash equal to minus P cos theta plus P cos theta dash. From this formula, theta dash is 90 degree. Theta dash is 90 degree means what we will get? We will get here minus P cos theta plus P cos 90 degree. We know that 90 degree means what? Cos 90 means 0. Cos 90 means 0. So that potential energy U is equal to what we will get? Minus P cos theta. So U is equal to minus P cos theta. We will get when this theta dash is 90 degree. We know that we have learned that when theta is equal to 90 degree, this dipole is experiencing the maximum torque when theta is 90 degree. When the dipole angle is 90 degree, what will happen? Initial angle is 90 degree. It experiences maximum torque. That is what we have learned the last derivation. Torque experienced in a uniform magnetic field. So maximum torque experiencing, but here what is happening to this potential energy? So here minus means minimum potential energy. So that is what from this derivation we are proving. So torque when the initial angle is 90 degree, this dipole is experiencing maximum torque, but that time what is happening? U is equal to minus P cos theta we are getting. U equal to minus P cos theta means minimum torque. At the same thing, when theta is equal to pi means what? When this theta is equal to pi, we know that so pi or 180 degree you can keep. So U is equal to, how we will find minus P cos, what will happen? 180. We know that cos 180 is equal to minus 1. So U is equal to minus P into minus 1. So U is equal to minus P instead of cos 180 minus 1. So U is equal to what we will get? Minus into minus P. So you see potential energy. Potential energy is maximum when theta equal to 180 degree. But torque, what will happen? Torque is minimum. This is what we are proving. When theta is 90 degree, what is happening? It experience this dipole experiencing maximum torque that we already proved. When the theta is 180 degree, this torque experiencing is minimum. So when the torque is maximum, potential energy stored is minimum. When the torque is minimum, potential energy stored is maximum. So this is what we are proving from this concept. Okay. So dear students, again you can go through this, take a screenshot of this derivation and learn this. All of you take a screenshot on this electrostatic potential energy of a dipole in a uniform electric field. Take a screenshot on this derivation Then this also case, like a case only. So take screenshot on this and study this thing. And the next important thing is electric flux. Electric flux. So before that, you can mark those who have the textbook. You can take page number 35. Those who don't have the textbook, you can take a screenshot of this page. Electrostatic potential energy of a dipole in a uniform electric field. The next page I'll show you. So take this screenshot and study this. And the derivation, what I shown in the notebook, you can you can take the screenshot that also. Now next class we will see this electric flux. So today itself you note down this derivation on your notebook and learn this. And see you all. Bye bye.